In this video, I'm going to go through A-level Chemistry Paper 2 Edexcel from 2018. This is the second half of the paper. I'm starting off on question 7. I covered the first half of the paper in an earlier video. Okay, so first question is a big organic synthesis question. Okay, it says phenylethyne, which is this stuff here, used to make polystyrene, used in packaging, can be made from benzene in a 3-stage synthesis. Here they give you some of the compounds that you can use, and you've got to devise a synthetic pathway. And we've got to draw the structures of A and B, state the reagents and conditions for each step. Okay, so I'm going to first of all just pick up some sort of go down the wrong way a little bit, just to show you the possibilities and the thought processes, rather than just going straight to the right answer. Right, so obviously we've got to stick on a 2-carbon unit onto benzene. Right, let's have a look at 2-carbon units we've got in our list of reagents. So we've got chloroethene, we've got ethanol, we've got ethanol, and ethanol chloride, and ethene. Okay, ether is a solvent. Okay, so I suppose the most obvious thing you might think is, right, let's stick an ethene, because then we've done it. Stick an ethene onto the benzene ring, but we don't know any way of putting an ethene onto a benzene ring, so that's a non-starter. Likewise, I don't think you'll be able to think of a way of getting ethanol or ethanol onto a benzene ring. So it leaves us with chloroethene and ethanol chloride. Let's think about chloroethane. Could we stick that on? Well, we could, because if you get chloroethane, and you react that with an aluminium chloride catalyst, you will generate this electrophile, which can then react with the benzene ring, electrophilic substitution. This is positively charged, so it likes the high electron density on the benzene ring, and that would end up giving you ethyl benzene, and then you'd have to somehow create a double bond between these 2 carbons, but I don't think we can do that. There's no way we know of turning an alkane into an alkene, so that is a dead end. So that leaves us really with the ethanol chloride as the 2-carbon unit we can stick on, and that is the right one. So the ethanol chloride has got this structure, and we are going to react that with aluminium chloride catalyst, which will generate this electrophile and AlCl4-. This electrophile can then react with the benzene ring, electrophilic substitution, so you're going to swap one of the hydrogens on the benzene for that. So we have now got this. Now we've somehow, so the conditions for that first step is going to be, you want the ethanol chloride and you want the aluminium chloride catalyst. That's the conditions for that. And this will be what A is. That's A. Okay, so somehow we have got to turn that into the ethene group. So now it's a bit of a clue here. Let's cross out some of these reagents we've used, so we don't want to worry about that anymore. That, all of these, we don't want them. So what have we got here? We have got lithium tetrahydroaluminate, and now if you remember what that will do, will that react? It won't react with a benzene ring, but it will react with the carbonyl group. It will reduce the carbonyl group to an alcohol. Now you've got lithium LiAlH4 is essentially, you've got a hydride ion. and that hydride ion is going to attack nucleophilic addition. It's going to attack that carbon there. So that's what's going to happen in the next step here. So I'm going to write down, this is going to be B. We've reduced it to this compound. So we're going to have, that's going to be an OH now. Sorry, that is just going to be an H, and this is CH3. Okay, so and the reaction conditions for step 2 then, it's going to be a lithium aluminium hydride, LiAlH4, and you may remember that's always got to be in a solvent of dry ether. So we've used up the ether there. In ether, that's the condition for that. Finally, step 3 then. So somehow we've got to convert, and I'll clear a bit of space here. We've got to convert this alcohol into an alkene. So we've got to turn that into, draw it in blue. So what have we done there? Well, we've got to remove an OH from that carbon and an H from that one. We're dehydrating it, we're removing the water. And you may remember, well, the best reagent to do that is concentrated phosphoric acid. And what you're going to have to do is reflux this. So we want conc H3PO4 and heat under reflux, and that will do it. Okay. Let's move on to the next question. Okay, which reagent could produce a diol from phenylethene? Okay, so we've got to think, we've somehow got to stick 2 OHs on that. What will do that? Well, you can oxidize it with, and you've got to use potassium manganate 7. That's a test. That's another test for an alkene group. Acidified potassium manganate, which is purple, it will change. It will lose its purple color. That's the oxidizing agent that will do it. It is an oxidation. Acidified dichromate won't work. I don't know. It's not a strong enough oxidizing agent, but doesn't oxidize it. Acidified potassium manganate will do. Okay, so this is kind of not really a chemistry question so much. One advantage and disadvantage of disposable polystyrene by incineration. I would say, right, advantage is no landfill. Disadvantage, right, if you don't burn it at a high enough temperature, you can get toxic organic compounds possible if it's not burnt at a very high temperature. You produce organic compounds, some of which will be toxic. Right, calculate the percentage mass of carbon in phenylethene, giving your answer to a okay, so what have we got here? We have got phenylethene. So we've got 6 carbons in the benzene ring, 2 others, so that's C8. We have got 5 hydrogens on the benzene, 5, 1 there, 6, plus 2 more, that's 8, H8. Okay, the percentage mass of carbon, so the MR of that is going to be 8 times 12 plus 8, 104. Of that 104, it's 8 times 12 is carbon, 96. So the percentage carbon is going to be 96 over 104 times 100. Right, now that gives us 92.3%. Should we give it to 2 significant figures or 3 significant figures? Well, really, we're only given, we're using the MRs to 3 significant figures, because we do know carbon is 12.0, hydrogen is 1.0. So yeah, 3 significant figures, 92.3. Phenol is a feedstock in the production of many organic molecules. Okay, phenol reacts with bromine water. Complete the equation for the reaction of phenol with excess bromine water using the skeletal formula of the organic product. Well, you've got to know this really, that what happens is you're going to get bromine is going to add at these positions, at position 2, 4 and 6. It always goes to those. And put the last one in. And what happens to those hydrogens that come off? They come off as HBr. So you're going to get 3 HBr. So that means we're going to need 3 bromine 3s, so we need 3 Br2s. We've got 6 bromines altogether. Right, compare and contrast the bromination of phenol with bromination of benzene. Okay, so we should know here that, first of all, phenol undergoes electrophilic substitution more readily. And the reason for that is the lone pair on the oxygen is also partly delocalized. Localized on the benzene ring, and so that means increased electron density on the benzene ring, particularly at positions 2, 4 and 6 actually. That's why it always goes there. So that means phenol is more reactive. So it reacts more readily in electrophilic substitution reactions. That means with phenol, you can use bromine water and no catalyst is needed. And you don't need to heat it, room temperature. If you want to do that with benzene, because it's not as reactive, you can't use bromine water, you have to use bromine liquid. You need a catalyst, usually FeBr3, and you have to heat it. It won't happen at room temperature. And you will probably not get multiple substitutions. You'll only get 1 bromine sticking per benzene ring. So there's enough there to cover the 3 marks easily. There's more than that. Okay, so phenol is basically a lot more reactive than benzene because of that lone pair being partly delocalized. Increases the electron density, electrophilic substitution happens a lot more readily. Okay, phenol can be nitrated to produce 4-nitrophenol. The mechanisms of the nitration of phenol and benzene are similar. Complete the diagram using curly arrows to show a possible mechanism for the reaction between the electrophile and phenol to produce. Okay, so I'll do that here a bit bigger so you can see. Right, so we've got OH there. We've got NO2 as the electrophile. Right, one of the pairs of electrons is going to come out of the benzene ring, the delocalized system, onto there and form a bond to the nitrogen. So the intermediate is going to be like this. We're going to have OH there. We're going to have the NO2 stuck on there. And to remind ourselves, there's a hydrogen in everything, but there's one there. We're going to remind ourselves that it's there. The delocalized system is broken partly, so we're going to draw that partly broken. And of course, this has got to have a positive charge somewhere because the phenol is neutral, the NO2 is positive, so that thing has got to have a positive charge. And the positive charge is shared over the delocalized system, makes it more stable. And the final step of the mechanism, that pair of electrons from the bond there goes back into the benzene ring to reform the delocalized system, and you're going to get the product. Okay, and you're going to get an H+ ion. Okay, so you probably get a mark, one for each 3 marks, 1 for each curly arrow, 1 for the correct intermediate, the structure of the intermediate. Okay, what is the mass in grams of 4-nitrophenol produced from 0.94 grams of phenol if the yield is 15%? Okay, so we need the phenol. C6H5OH. The MR of that is 94. And for nitrophenol, sorry, I need to put a OH on there. Right, so what we've done, we have got an extra NO2, so that weighs 14 plus 32, that weighs 46, but then we've lost the hydrogen from there, so we add an extra 45 to 95, which gives us 139 as the MR. Okay, so the moles of phenol, mass over MR, 0.94 over 94 equal to 0.01 moles. It's a 1-to-1 ratio. 1 mole of nitrophenol gives, so 1 mole of phenol gives 1 mole of nitrophenol. So moles nitrophenol, that's going to be equal to 0.01. The mass of nitrophenol, if you get 100% yield, is equal to moles times MR. So that's 0.01 times 139, 1.39 grams. But we only get a 15% yield. So with a 15% yield, we do 139 multiplied by 15 over 100. And that gives us 0.21 grams. So B is the answer. Okay. Do two structural isomers of nitrophenol which have a benzene ring. Okay, so for nitrophenol, so for nitrophenol, so we can have 2 nitrophenol, and we can also have 3 nitrophenol. So that should be an OH there. So it's a draw them, okay. So that's what, yeah, if I'd put the phenol there, obviously it's the same as having it on that one there. All right, so it's got to be on that one. Oh, there would be, you could draw it there as well. Okay, so those 2 are the answers. Okay. Right. Right, this is about the reaction kinetics of an iodine clock reaction. Okay, one example of an iodine clock reaction involves the iodate ions and iodide ions in acidic solution, is this, okay, and you're going to make iodine, I2 there. State why the order of reaction with respect to iodide ions cannot be 5, even though 5 moles of iodine is shown in the equation. Right, so you can see there. So you might think, oh, it's 5 moles of iodide react with 1 mole of iodate, but the chances of that happening are so slim that it is obvious that can't happen. You cannot have 5 iodide ions colliding with 1 iodate. The probability is too low, so the mechanism cannot go in that way. Okay, a series of experiments was carried out to determine order of reaction. The concentration of iodide ions and the acid were in a large excess, and the volume of iodate was varied. Okay, the total volume of the reaction was kept constant by addition of suitable amounts of water. Okay, and the following results were obtained. Okay, right. So what you've got to do, I think, where does it say that? Question 2. All right, what you've got to do, is you have got to fill in these answers here. So that is going to be, so you do 1,000 over the time taken. So you do 1,000 over 260. That gives you 3.84. That gives you 2.80. 1,000 over 606 gives you 1.65. That's all to 3 significant figures. And then in the next bit, it asks you to plot those on a piece of graph paper. And you have to plot against, on the x-axis, you have got concentration of of iodate. The volume of iodate is actually proportional to the concentration. And here you're going to have the rate. That's 1,000 over time. And you have to plot them. And you end up with a fairly straight line graph. I think one of them actually goes right through the origin. That's the origin, 0. It's a straight line. One of them is a little bit out, so you should just not draw a straight line through that. You get a mark for that. And then it says, what is the order with respect to iodate ions? Well, from this graph, this should be a straight line. It's first order. And they ask why. Well, you can say, you've got to say, you get a straight line which goes through the origin. Through the origin is quite important, okay? And that means it's directly proportional. That means rate is directly proportional to the concentration of iodate. So that means it must be first order. If it was second order, of course, you'd see something like that, a curve. Okay, in experiment 6, the student forgot to add deionized water to keep the total volume the same for each experiment. Why the total volume should be kept the same? Right. This is so that well, there's two reasons. One, really, so that you don't change the concentration of H plus and I minus, so that you're only investigating the effect of that. But they did say they were both in large excess, so that might not have so much of an effect. So the other reason, which I think is probably it's only a 1 marker, is to say that so that the concentration of iodate is directly proportional to the volume of iodate solution that you add. So here we add 10, 7, and that stops you. That means you don't have to work out the real concentration. You can just, on this graph, you can just plot 10 is proportional to the iodate concentration there, 1 is proportional to it. So I would go for that reason. If it was a 1 marker, that's the best reason that there. But usually it's also so you don't change the concentration of the other reactants. You add water to keep them the same. Right. Okay. Right, onto this bit now. So this is straightforward, putting numbers into a rate equation. Okay, so the reaction is first order with respect to hydrogen peroxide and iodides, but 0 with respect to hydrogen ions. Write the rate equation. Got to write the rate equation. So we've got the rate is equal to the rate constant. It's first order with respect to hydrogen peroxide, first order with respect to iodide, but 0 order with respect to hydrogen ions. So you don't need to put that in because, of course, that's pyranol. It's just 1, so you can leave that out. There's your rate equation. Then it says deduce a value of the rate constant. So K, we rearrange, you get rate over hydrogen peroxide times iodide, put the numbers in there. The rate they tell us is 1.24 times 10 to the minus 3. Hydrogen peroxide concentration, 1.50 times 10 to the minus 3. And iodide concentration, 2.1 times 10 to the minus 3. Put the numbers into the calculator, we get an answer of 393.6. Now we'll think about the significant figures. Okay, Well, all the data is given to 3 significant figures, so we should give ours to 3 significant figures. So that should be 394. And the units, well, the units, let's just see, we've got to think about that. The rate of units is always mole per decimeter cubed per second. The units of hydrogen peroxide concentration and iodide concentration are both moles per decimeter cubed. So we're going to cancel that mole per decimeter cubed out. So we get seconds to the minus 1 over mole dm to the minus 3, second to the minus 1, mole to the minus 1, dm to the plus 3. They are the units. Okay, now explain the purpose of the starch in the reaction mixture when starch is neither in the rate equation or the reaction equation. Right, the reason why we use starch is because starch it reacts with the I2 to form a blue-black complex, and it intensifies the color of the starch. So rather than being a pale brown, it's a very pale brown, which is the color of iodine in aqueous solution. It's a very strong blue-black color, very easy to see, even at low concentrations. Right, now we've got, looks like an Arrhenius equation. Okay, so another iodine clock reaction produced data that enabled the following graph. Okay, so the Arrhenius equation is here. They always give you that whenever you don't have to remember that. And so we can see, you should know from that, well, we've got ln K is equal to minus EA over R 1 over T plus the constant. So we plot ln K on the y-axis, we plot 1 over T on the x-axis, and the gradient is minus EA over R. Okay, so we've got to use from the gradient determine the activation energy. So let's do that. So I'm going to draw this construction line here. I'm going to just, by the way, let's just get this question out of the way first. Why do they ignore this point? Well, it's not on the line, so it's anomalous. So that's pretty straightforward. Get rid of that. Let's work out EA. Right, so we've got this triangle here. And work out the gradient, the graph. Change in Y, change in X. Change in Y, well, we have got minus 8 down here, minus, and that's like 0.2, minus 0.2. That's equal to minus 7.8 for the change in Y. The change in X, it's a negative gradient, obviously the way it's going. Well, we got there is 1.7 times 10 to, 1.7 times 10 to the minus 3 minus 1.3 times 10 to the minus 3, which is equal to 0.4 times 10 to the minus 3. The gradient m is going to be changing y over changing x, so we've got minus 7.8 over 0.4 times 10 to the minus 3. That gives us a value of minus 19,500. Okay, now we know that the gradient we know that m is equal to minus EA over R, so therefore EA is equal to m minus m times R. So we have got m is 19,500 and R, now that's 8.31 joules per mole per Kelvin. That's important that it's joules because it's going to give our answer in joules, not in kilojoules. Okay, so minus E is equal to minus minus, that makes it a plus. Multiply that out, you get plus 162,045 joules per mole. And let's turn that into kilojoules, give it to 3 significant figures. We have got 162 kilojoules per mole is the activation energy. And that is the end of the paper.